Hello and welcome to Machine Learning First Steps. Today we're going to work on a case study of neural networks. So we're going to classify objects based on their appearances, and as Agent Smith says, appearances can be deceiving. So this session is presented to you by Summer. So what are we going to do in this tutorial? We're going to work on a multi-class classification problem. Our robot is supposed to distinguish between two specific classes, which happen to be dogs and cars. We're going to implement neural networks using Python, and instead of just writing our own implementation for neural networks, we're just going to use TensorFlow because it happens to be so much easier, and there are a lot of implemented APIs that we can use right away without having to implement them from scratch. The basic requirements we're going to have today is we are going to install the pill library in case you didn't do that already. In case you have them installed from our last session material, then it's okay. We're going to need also the pandas library in case they are not installed in your virtual environment. You can install it using conda. And of course, you need to download the tutorial files and save them in a directory because you will need to open these files using your IDE. And of course, run your Spider IDE and open up the project. So let's go. So now I'm going to open up my Spider IDE. And today we are going to use TensorFlow instead of just implementing everything from scratch ourselves, because TensorFlow is much easier to use than just implementing everything yourself. And we've got two important files, which is this doggercar.py. You'll find it attached in the session files. So this is basically where we're going to collect our data set. So currently we have a bigger data set that includes photos of both cars and dogs, and much more photos than the number of photos in our last session. So right now, instead of just writing the code, which will take significantly more time than displaying it, so I'm going to display the code without writing it all over again. But I'm going to go through every line and explain the details or explain the exact syntax of that line. So first of all, I'm going to start with the libraries that I need. So I need a library called NumPy. We already know that. There's another library called pandas, which happen to do with something called data frames. So whenever you have an Excel sheet that you want to read from, or you happen to want to group your data in a format called data frames for plotting or something like this, this is when we use this library, and we're going to use it for that specific purpose that I said before, which is basically gathering our data in data frames for plotting our learning curves. And of course, I'm going to import the dataset collect function from my doggercar file, which just converts my images into usable NumPy arrays that I can use for training. And today I'm going to import TensorFlow, and because TensorFlow is such a long name, I'm just going to import it as TF instead of TensorFlow. And I'm going to import some utility from TensorFlow known as TensorFlow.keras.layers. So instead of typing tf.keras.layers, which also happens to be kind of long, I'm just going to import it as TFL instead of just typing tf.keras.layers, just for saving time. And it might look weird because I'm importing TensorFlow as TF, and at the same time I'm importing one of TensorFlow's utilities, which sounds redundant, but it's not, because this specific utility here, this specific object here, is very long as well, so it needs a name of its own. And I'm going to import TensorFlow, I'm going to import a certain feature from TensorFlow to Keras called regulizers. And for those of you who might be aware of machine learning platforms, well, Keras, as some people might know, used to be like an independent platform, but now it's part of TensorFlow. So Keras is like an abstraction of TensorFlow itself. So it is a higher level of TensorFlow that allows you to deal with neural networks in a much easier way than the normal TensorFlow itself. So basically, we can consider Keras as part of TensorFlow or some higher form of TensorFlow, basically. And so TensorFlow has an object called Keras, and Keras is an object called layers. So we're just like importing something from something from something, that sort of thing. Then I'm going to have a function here called convert to one hot. And what this function does is that it takes the raw classes or the raw definition of classes from my data set collect function, which happens to be of the form 0 or 1. 0, for example, for car, and 1 for dog, or maybe the opposite. I can't really remember. But anyway, we have a class which takes the label 0 and another class which takes the label 1. So what I'm going to do here is that I want to convert this raw form into a form that is usable by TensorFlow, which is called one hot. So instead of having, for example, an array of zeros and ones, maybe something like this. So, for example, car, dog, dog, car, or maybe the opposite, dog, car, car. Or did I reverse it? Anyway, doesn't matter. You get what I mean. So instead of that, I'm just going to get a matrix which happens to have some rows and columns, something like that. And for each row, I'm going to indicate which class happens to be true. So the class which is false will take 0, and the class which happens to be the true for this particular example will take 1. And here, for example, 1, 0, and 0, 1. So the difference between both forms is that in this one hot form, each row represents a training example, and we have like a label for each class. So, for example, I could have 0 and 1, which means this particular example holds a value which is false for dogs, for example, and true for a car. But here we get the opposite for the second example. So we have a value that is true for a dog, for example, and false for a car. And I'm not really sure if I reversed that as well. So this is particularly this example is the opposite of this example. So here, if a car happens to be true, then it happens to be false here, and a dog is false, so a dog will be true in here, and so on and so forth. So this one hot representation is what TensorFlow actually deals with. So we can't use just the raw form, which dictates that this example has a label which is 0 or 1, 0 for dog, 1 for car maybe. This is not how TensorFlow works, so I need to convert it to this one hot representation, which assigns like a probability for each individual class for each example. So basically what I'm going to do here is that I wrote that implementation for the one hot representation. So I just used the NumPy utilities in order to create a function which converts this row class array into something more usable, which is the one hot form. I'm not going to explain the exact details. It's a really simple function, and you can implement it yourself. So I'll leave it as an exercise for you to understand how I wrote this function or how this function works, and maybe you can manage to write your own implementation, since this doesn't happen to be actual machine learning, just converting from one form of arrays to another form. There's another function which does the exact opposite, and actually I don't think we're going to need this function for this exercise, but I threw it anyway. So this is convert from one hot, which converts the one hot representation back to its raw form. Then we have the model function, and this is pretty important because this is like the core of TensorFlow itself. So instead of just implementing neural networks using an implementation that's been written from scratch, I'm going to use a function called model, which is going to be the template for my neural network here. So basically, you have to determine something called an input frame and an output layer. So your input frame represents the shape of your inputs, or the form or the format of your inputs. So I'm going to use an object or a utility called tf.chars.input, and it takes an input argument, which is the shape of the input itself, or the size of the input. So basically, because we're having an image here, and then I flatten out this image's elements into one array, so I'm going to feed the size of that input array or input vector feature to this function. And I'm not actually feeding the vectors of all examples all at once. I'm just dictating what the input shape for a singular or individual example is. So basically, if I have an input vector which happens to be of the size 60 times 1, for example, then I'm going to declare that the shape is 60 times 1. But I may have 1,000 examples, for example. I'm not going to include that 1,000 as part of the shape. Then I'm going to include my hidden layers here. So for this particular layer, I'm using an object called dense, which basically refers to a fully connected layer, or something we call a dense layer, or just a group of logistic regression units grouped together in like a vector form or something, as we explained in the little lecture we had before. So basically, I'm having a hidden layer containing 500 neurons or 500 elements, and the activation function I'm going to use here is ReLU, since ReLU happens to be very effective in learning, maybe even more than tanh or sigmoid functions for most applications. And I'm going to use a regularizer. So here I'm just going to indicate that this regularizer is of the type L2, which means I'm penalizing the weights, basically. So I don't want the model to overfit, and at the same time I don't want it to underfit. So I'm picking a regularization parameter here, or a regularization constant of a value of 0.03. I didn't quite tune these parameters. I mean, I tried quite a few parameters, but I didn't conduct an actual hyperparameter tuning session for this example. I'm just trying to show how we construct our neural networks and how we train them. But the topic of hyperparameter tuning and hyperparameter selection is a broad topic that may be discussed in a more advanced course. So we'll just take these parameters. They may not be the optimal parameters, and as a matter of fact, this is quite a small neural network for an image processing application, because usually we use more complex networks, and we use like different networks like CNNs, for example, for this sort of application. But we're just going to use this particularly small neural network for this application for the sake of just learning. And then after determining my parameters here, I'm going to dictate that this layer here takes its input from the input frame itself. So that means this hidden layer or this hidden layer's input is the input to the whole network, which means this is layer number 1, for example. So I call it F1 to indicate that it's just the first hidden layer. And actually we have one hidden layer here, so it's the first and last hidden layer. So this format, or this we can call it format. This format of model structuring is called the functional API. We've got two types in TensorFlow, one called the sequential API and one called the functional API. I use the functional API all the time because it happens to be more versatile and it's almost suitable for any application. So we'll just use this functional API formatting for this particular example. Then in the end, I'm just going to structure my output layer, and it's going to have 2 units because I'm basically trying to output one of 2 classes, or I just have 2 classes here. So basically I have 2 decision units, we can call it that. And as we said before, usually for the last layer we pick a type which is called softmax, which is pretty close to sigmoid but not quite the same. It basically outputs values that are bounded by 0 and 1. So basically it just outputs probabilities just like a sigmoid does, but they have slightly different structures. But we usually use softmax layers for this final decision layer, or for the output layer. So we're going to stick to softmax for this example. Actually, this is wrong. It has to be 2 neurons in output layer. And this actually has to be softmax. I had so many iterations here, so maybe some of the comments may be outdated. Yeah, I think we don't have any other comments. Yeah, basically, we're good to go. All right, so then the next thing, I'm going to define an instance of the model. So basically, I'm just dictating that this structure here is going to be maybe a model class or something like that that any user could use later by using this model function. So I'm going to dictate that the inputs to my model, or any instance of the this model, is going to be of the size input frame, and the outputs are going to be output layers. So basically it's just like the input and output arguments of a function, something like that. It may be a little bit peculiar because it's a special function of sorts, and we're using TensorFlow, which doesn't have quite the same standards as usual APIs. But you can just copy this as a template. You don't have to concern yourself with the exact details of how these APIs were implemented. You're just going to use them as is, and you're just going to change like the input arguments. Maybe this layer's, for example, this layer is pretty standard. You don't change that. Maybe the dense layers in between are the ones you're going to change, and not all of them. You're just going to change, for example, the parameters, like the number of hidden units, the activation functions, the regularization parameter maybe, and maybe for the output layer, just gonna change the number of output units. But basically, you're going to copy and paste this function as is most of the time. So what I'm going to do now is that I'm going to go through the code itself. So first of all, I'm going to extract my data set. So I'm going to use the dataset collect function, and same as before, this function has been already implemented for you. You don't have to re-implement it. So it basically takes the images and converts them to NumPy arrays that we're going to use. And we've got the training input features, the training outputs, the test input features, and the testing outputs. Then I'm going to flatten the input features because, as we said before, the images are of the size number of pixels times number of pixels times 3. So we need to change that, or we have to flatten the input features. And then I'm going to scale my data set to obtain better results. So instead of having pixel values that range between 0 and 255, we're just gonna make them bounded by 0 and 1. And then we're going to use the convert to one hot function in order to obtain a one hot representation for the training and the testing labels. So because TensorFlow basically, as we said, needs one hot representations instead of raw labels. Then I'm going to use the helper functions that I created before. Basically this model function, which is basically a TensorFlow function of sorts. And I'm going to create an instance of this model. And I'm going to call it neural network model. So basically this model is like a class, or this function now is like a class. I can create millions of instances of the same class, like for example this object here or this instance here. So I can create more models if I want to of the same type and the same exact structure. And I'm going to feed the input argument here, which is the shape of the input. But because my train X, or my training input features, are of the size, for example, they might be of the size like number of examples, maybe, and then the number of features, as we said before. So it's basically M times N here. So TensorFlow only needs to know this part. So I'm going to include the size starting from index number 1. I don't need index number 0, which is the number of examples. So it's going to be, TensorFlow will read it like this. Basically, it's interested in this part, so I don't have to care about the first part, which is why I'm feeding the size here starting from 1 till the end. This means type the shape from index number 1 of the shape till the end. So basically we have two axes for the shape here, so I'm just going to take the second axis up to the end, which is the second axis already. So it's just like I'm passing on just one part of the shape, which is the other axis. Sometimes, or some algorithms use more complicated shapes, like shapes that are composed of the number of examples and other axes combined. So this is why I basically use till the end here, this part, which means till the end, because it helps me like create a more general input size for any application. If you just want to pass 1, it's okay. It will be the same thing, basically. Then we're going to compile our model. We're going to use a function or a method called compile. So what I'm going to do here is I'm going to indicate what my learning algorithm for this application is going to be, and the learning rate that I'm going to pick, and the loss, or the type of loss, and some metrics as the accuracy, for example. So most of these terms you're not familiar with because the learning algorithms here tend to be more complex and adaptive. So they are not like the standard gradient descent that you've studied before or that you've seen in this course. You might find more adaptive and more complex learning schemes that may be much faster than gradient descent or just have better results. And it's up to you to choose which learning scheme suits you best. Actually, we have standard gradient descent. I can just include the standard gradient descent that you know, and it's called SGD. But I found that this 88 delta learning scheme is better for this example. And it's not a matter of actually knowing how this algorithm is implemented. It's just that I tried so many optimizers, and this seemed to be the best one. And I'm going to include the learning rate, which I picked to be 0.05 for this example. Then I'm going to determine the loss here, or the loss function for each example. So here, instead of just using the normal loss function that you saw before, you can actually pick a number of loss functions. For multi-class classification, we usually use categorical cross entropy. This happens to be the best loss function. There are other loss functions that you might use as well. And for just like binary classification, we pick a loss called binary cross entropy, which happens actually to be the same thing as the losses that you've seen before, but there are actually other types of losses that you can use as well. Many losses other than binary cross entropy and categorical cross entropy. So you needn't concern yourself with the exact details here, because this is more of a standard thing to use, like categorical cross entropy for multi-class classification and binary cross entropy for binary classification. And then we're going to pick a metric here, which is accuracy. That means I'm going to show the accuracy automatically. So like how many examples out of the many examples that were provided in the training and testing data sets I managed to get right. So this is basically a metric that's going to show up during my training session, as we're going to see when we run the code. And this is something called the model summary. So this is like a print statement for the structure of the model. So it's going to show in your console here how your model looks like, in case you want to like review the exact structure of the model, in case you want to update something, or in case you made a mistake for one of the dimensions, for example, or something like that. It just provides a summary for what you did. And then we're done with the model construction part, so we are going to shift to the model training part. And for the model training part, you need to first convert your training and testing datasets into tensor objects. So you're going to use an API or some utility called tf.data.dataset from tensor slices, which is a very long name. Actually, you can rename it in the import section if you want to. And I'm going to, what this basically does, it just squeezes your training and one-hot representation of the labels into just one tensor object that is a dataset tensor object. And you're going to determine something called the batch, which means basically, well, there are two types of learning here. This is out of scope, but there are two types of learning, something called the batch learning and something called the mini batch learning. We already know how batch learning works, which means that I get my entire training data set and I try to optimize the function using the entire training data set as sort of an input or sort of an input feature matrix. So all of the examples are included in the training simultaneously. But for mini batch applications where you have like huge, really huge data sets, and you can't just include all the training examples just all at once because they happen to be very big and you don't have the computational capacity for optimizing your loss function or your cost function with all of these training examples included simultaneously. So what you do is you divide your training data set into batches or mini batches, and you train your network using one of the mini batches at a time. So for each iteration, you use a mini batch. So this helps you like sort of divide and conquer. But because we have like a relatively small training data set, which happens to be, I think, composed of 1,000 training examples, which almost seems like relatively small to bigger, more complex applications. So I'm going to include the whole batch. So basically, I'm going to say that just include the whole training set size, which is basically the shape or the index 0 of the shape, which means just like the number of examples which are already provided by my dataset collect function. So I'm going to just take the whole batch. And the same thing goes for the test dataset. So I'm going to also define a tensor object for my test dataset, and I'm going to include the whole testing batch as well. Then I'm going to use a function called model.fit, or just fit. So what this function basically does, it takes your testing and your training datasets, which happen to be the first and the third arguments. So basically it's going to use the training dataset for the optimization process and the validation dataset or the test dataset for validation. So it's not going to use this test dataset for training. It's just going to use it for like validation, or validating your network for unseen data basically. And I'm going to determine the number of epochs, which is basically the number of iterations. So I'm going to pick the number of epochs to be 1000. Then I'm going to use some plotting functions. I'm going to use the pandas library for just creating data frames out of the history. So the history happens to be like the output of the fitting function, which contains all the information, all the training information, and the list of accuracies for each particular epoch, for example, and the evolution of the loss function. So this happens to be a very big object which contains a lot of data. So I'm going to just like break it down into training losses, validation losses. So I'm going to see how the loss function works or changes for both training and testing data sets, as well as the accuracies. So the loss function is basically the function that we saw before, which is the cost function, basically, J. Sometimes, well, here we sometimes call it the loss function, but it's actually the cost function. It's not for just one example, it's for the whole batch you provide. So this might be a sudden change in terminology, but you shouldn't care about that. It's just the cost function. And I can actually change this to be the cost, but sometimes in like TensorFlow documentations, they use the term loss for cost or instead of cost. So we actually never use the loss for an individual example in a machine learning platform. So loss and cost here are interchangeable, and they both mean the cost function. And I'm going to also display the accuracies. So that means how many examples I managed to get right. With respect to the whole set of examples provided. So next thing, I'm going to run this code, and it's going to take a little while. So now the training is done, and we can see that our loss function for the training examples reached a value of 1.19 or almost 1.2. And it started with, I don't know, the console can show all of the epochs, so we're just going to stick to that, to the final output now. And our training accuracy ranges between almost, something like 87% and 92%, so it's quite noisy because we didn't tune our parameters very well. And we got a validation loss, which is 1.3, which is basically very close to the loss. So we can say we don't have much variance here. And we've got a validation accuracy of almost 88%. We can also see the graphs here. So we can basically see that the loss function or the cost function started at around 30 and started to decrease till it reached almost 1.2 for the training and 1.37 for testing. And we've got the accuracies listed here, so we can see that on average the training accuracy might be something around 92%, and on average here the testing accuracy might be something like between 85 and 87%. Yeah, more like 85%, I'd say. So that means we are getting like 85% of the testing on scene examples, right? Which is not pretty bad and not pretty good either. But it's kind of good for this really small neural network because we have only one layer. Usually we use more complex neural networks for this sort of task. So this is basically it. And I hope you could now use this code maybe for other machine learning applications as well. And we're actually going to work on some future example using a more complex network scheme later. To summarize what we did today, we now understand how to implement basic classification problems, both using our own from scratch implementations and using TensorFlow's APIs. But since you're already familiar with how things work right now, you just need to write your code the easy way and the fast way by using TensorFlow APIs. So congratulations on your second project, or maybe third project, I lost count. I need also to include the references for the datasets I used for this tutorial. So basically I was relying on Stanford datasets for both dogs and cars, in case you're wondering where I got these images. So thank you for your time.